Chapter 10 is all about hypothesis testing. So understanding how to set it up correctly is a big part of that. And when you read through the question, you're looking for what was stated before and what are you testing newly. In this case, we have students enrolled in a 2-year public institution. The proportion who earned bachelor's degree within 6 years was 0.399. And the president of a certain college believes the proportion of students who enroll in her institution have higher completion rate. So the president thinks it's going to be higher than that, but 0.399 has already been established. Therefore, it's the null hypothesis. In this case, we have 0.399, which is like a probability or a proportion, that kind of thing. That's why it's P. We're not talking about some kind of number that's describing the whatever the sample that you're working with. That would be mu. And then we're not talking about a standard deviation either. So it's a population proportion. The null is equal to what's been established. And the alternative in this case, the president believes the proportion is higher. Okay, so she believes it's greater than 0.399. That's how you establish the null. And then the alternative is what you want to test, what you want to find out. Now, type 1 and type 2 error all depend upon either rejecting H naught when it's true or accepting the alternative when it's not true. And which one's which? Well, if you go into the textbook, there's a table that can help you figure that out. So we're looking for the table. And it's this right here. So we have the conclusion and reality, right? If we do not reject H naught and H naught is true, then that means we have the correct conclusion. If we reject H naught when H1 is true, then we have a correct conclusion. There's only 2 other possibilities, and that's what type 1 and type 2 error are. So for the first question, it says, which of the following is type 1 error? And it says here, type 1 error is when we reject H naught when it's actually true. So of the 4 possibilities, only 2 of them are where we reject the hypothesis, the null hypothesis. It's going to be C or D. When the null hypothesis, which is where the population proportion does in fact equal 0.399, that's what part C says. It says when in fact the proportion is 0.399. So we reject the null hypothesis when it's actually true. That's type 1 error. Type 2 is where we do the opposite. We fail to reject, so it should be C or D again, where we fail to reject when in fact the alternative hypothesis is true. So in fact, it's greater than 0.399. That's what D says. D says the population proportion is greater than 0.399, but we fail to reject this null hypothesis, and so we think it is 0.399. That's also an error, of course. Check that, and that's all correct. Now the next question, I believe, is very similar. Here we have 3 years ago, the mean price of an existing single home was this much. A real estate broker believes the existing home prices in a neighborhood are lower. That's the key thing to note there. So the null hypothesis, in this case, we're talking about a price, a mean price. That's why it's going to be mu, not a population proportion. And once again, we're not talking about standard deviation here. So it's been established that it was 243,707. That was the previously established amount. But now the real estate broker believes it's lower than 243,707. That's the alternative hypothesis. So same question, type 1, type 2. If you ever confuse those, just go back to the table. Type 1 says we reject H naught when it's actually true. So we're looking for reject the null hypothesis. So A or D rejects the hypothesis when it's actually true. So when it is the true mean cost. So we're rejecting this even though it's true. That's type 1 error. So then type 2 is going to be where we do not reject or fail to reject, C or D. when the alternative is actually true, when it is less than 243,707. So that is type 2 error. That's correct. Okay, a can of soda is labeled as containing 12 fluid ounces. Wants to verify the machine is not overfilling the cans. All right. No, this is a 12 fluid ounces. That's not a proportion. That's just talking about, like, it's a number that we're kind of basing all the things to be around. So that's what a mean is. It's all going to be around there, an average amount of 12 fluid ounces. So it's established that this should be 12 ounces. Now, what we want to see is it overfilling the cans? So overfilling is where it's greater than 12 ounces. If it were less than, then it would be underfilling, right? And if it says it's not filling to, or if it's not at 12, that would be kind of where it's not equal to. In this case, we're specifically concerned about overfilling the cans. So that's greater than 12. Okay. Quality Control Manager obtains a sample of 78 cans and measures the contents. So the evidence leads to reject the null hypothesis, or at a conclusion. So if we reject the null hypothesis, that means there was sufficient evidence that the alternative was correct. So there is sufficient evidence to conclude the machine is out of calibration. Okay, now suppose in fact the machine is not out of calibration, but we did reject the null hypothesis. So we rejected the null hypothesis, and when it actually is true, it is not out of calibration. So we reject H naught when it's actually true. Reject H naught when it's true. That's a type 1 error. Make sure I read that correctly. Yeah, we reject the null hypothesis when it's actually true. That's a type 1 error. But type 1 error has been made since we reject the null hypothesis when the null hypothesis is true. All right, management has confirmed the quality control, does not want to shut it down unless overwhelming evidence the machine is out of calibration. What level of significance would you recommend? So overwhelming evidence, that means we should, well, 0.1 is pretty easy to match, easy in quotes. 0.05, this is an alpha, as 0.05 is the kind of the standard one that you want. So that means that if you go even lower, if you make an even lower amount for the level of significance, 0.01, that means it's very hard to match that. In other words, you'd have to have a lot of evidence to show that, which is what they're saying, because this makes the probability of type 1 error small. Alpha, which is what we're talking about here, the level of significance, is the same thing as reducing type 1 error. And that's typically what we want to reduce in a lot of cases. All right. Okay. Previous year, 54% of females aged 15 and older lived alone. A sociologist tests percentage is different today. Tests whether the percentage is different today. So that's going to be the key thing. Whether it's different by having 500, a sample of 500 females, and finds 272 are living alone. Okay, so we're using alpha at 0.05. And we need to first see that we can actually use the hypothesis testing. So first off, NP1 minus P, of course, this is a population proportion, 54% of females, right? That's a proportion. So we're going to be using the proportion numbers, or formulas, I should say. 0.46 times N is 500. And we get 124.2, one decimal place, so... And this is definitely greater than 10. And since we're talking about like females here, age 15 or older, I mean 500 females is definitely smaller than 5% of the total population and over whatever country that you're talking about. There's no way that's going to be greater than 5%. So, okay, the sample is, okay, does it say anything about random? Yeah, conducting a random sample. So it is given to be random. And that means we can use hypothesis testing. They are satisfied the requirements. Okay, now we can set it up. We have the null hypothesis. That's what is given. 54% is what was given. So, and we're talking about a proportion. Alpha would never be in this, I'm pretty sure. Equals the given amount. And what we're testing here is whether a percentage is different. So we want the population does not equal 0.54. What this does is that it changes what we're working with from a one-tailed test, which is what we were working with previously, to a two-tailed test. That's the big kind of thing here. Okay, to find a test statistic, we have to open up StatCrunch. All right, and we have a population proportion. We can use the, let's see. We can use proportion stats, one sample with summary. We have all the information we need. See, 272 are living alone out of 500. So the number of successes was 272 out of 500 observations. And now we're talking about a hypothesis test. So here we want the null hypothesis to be 0.54, and we do want it to be does not equal 0.54. Okay, this is what we got. And the nice thing about this is it calculates everything for you. We have the z-stat right here and the p-value right here, which are the next two questions. 2 places for the z-stat is going to be 0.18. Okay, and the p-value is 3 decimal places, so 0.858. Yeah, okay. Now, what we're trying to do here, how you actually test this, the p-value is very, very simple to test, is what you want. This right here is the area underneath the curve. And if this is smaller than the level of significance, then there is sufficient evidence. That's why in the previous problem we were talking about, if you make the alpha level smaller, it's going to be harder for the p-value to be even less than that. So you're going to have to have even more evidence of it being the case. So in this case, 0.858, that's way bigger than 0.05. Therefore, we do not reject. There's not enough evidence to show. So do not reject. There is sufficient. No, you only say there is sufficient evidence when you reject it. So do not reject. There is not sufficient evidence to conclude that this number has changed from 0.54. And that's all correct. All right, 2 professors at a local college develop a new curriculum. So in a typical developmental math course, 51%, so this is going to be a population proportion, it looks like, of the students complete a course with A, B, or C. In the experimental course of 14 students, 10 complete the course with A, B, or C. So is it effective at a 0.01 level of significance? So first off, the null hypothesis is equal to what's been established, namely the 51%. That's a typical developmental math course. The experimental is the new one. It's the one that we're trying to experiment on or experiment with to see if it's better. That's why it's the alternative. In other words, this effectively what we're trying to do is figure out in the experimental course, 10%, is it effective? And so what you want to do is you want to figure out, is the population proportion higher? We don't really care about lower. We care about if it being better than 0.51. If it's the same or lower, then we know that we have to change it. That's the reason why we only care about if it's greater than 0.51. All right, So we got to verify the normal model may not be used to estimate the p-value. This is the important thing. It says verify that the normal model may not be used. And so this you should expect in P1 minus P. In our case, there's 14 students enrolled. P is going to be 51 times 0.49. And right there, 1 decimal place, that's 3.5. And that's less than 10. So that right there says that the normal model may not be used. So explain why this is a binomial experiment. All right, let's see what they have. There is a variable or fixed number of trials. So it'll be fixed number of trials with 2 mutually exclusive outcomes. Either they get A, B, or C, or they do not. It doesn't matter which one of A, B, or C they get or not. It's one or the other. Either they get A, B, or C, or they don't. So it's 2 mutually exclusive outcomes. You can't also get an A, B, and C and a D or an F. You can only get one or the other. And it's fixed because there's 14 of them. Okay, the trials are independent of each other, and probability of success is fixed at, I think it's fixed at the 0.51 for each trial. We'll check to see if this is correct at the end. Okay, p-value using the binomial probability distribution. So I think what we want to do is open StatCrunch. Go to a binomial calculator. N is 14, and we have our population of 0.51. Now, what we're trying to do here is we're trying to find for 10 completed the courses. So because we're looking for 10 being the tail, because right, we're working with the tail of the test. This is a little bit weird because we're not using normal distribution, but we're still kind of the same idea. You're looking for the probability, the area under the curve that's greater than the value, and the value we have is 10. That's where we're going to start with. So we're saying, what is the probability of any x that's equal to or greater than 10? And so what you can do is you can think of this number here as the p-value. That's what the p-value is in a normal distribution anyway. You're just finding the area underneath the curve for a certain distribution. And you can see this looks kind of normal, but the stipulation was not met. So I believe this is the p-value, and one's 3 places, so 103. Okay, and the level of significance is 0.01. And so this is greater than the level of significance, therefore we do not reject, because there is not sufficient evidence. If this was greater than the alpha level of significance, 0.01, then there would be enough, there would be sufficient evidence to reject it. So no, no, do not reject the null hypothesis because the p-value is greater than alpha. There is sufficient, no, I'm confused for a moment because I kept reading this as sufficient, but it says insufficient. So no, do not reject the null hypothesis. There is insufficient evidence to conclude that it's effective. So that's what we are saying here. P-value is greater than alpha, therefore we do not reject the null hypothesis. There's not enough evidence. All right. So now instead we're talking about 42 students instead of the 14 and 30 completed instead of 10 with A, B, or C. So now we can verify whether the normal mode may be used. Okay, so we have 42. And once again, we have the 51 times 0.49, 10.4958. That's going to be one place, so 10.5. That is greater than 10. So the sample size is definitely less than 5% of the population of all the students taking math classes. There's no way that's greater than 5%. So I think it's less than, it's reasonable to assume it's less than 5%. And the sample, let's see, does it say anything about randomness? It wouldn't really be random, but the professor didn't choose the students. They just enrolled in it. So I think you can say it's reasonably assumed to be random. That one seems kind of not really applicable to this because they choose to be in the class rather than it being random. So I'm not really sure unless they place them in there randomly. I don't know. We can't really use this whole thing if it's not random anyway, so that's why you can say it can reasonably be assumed to be random. So we may use the normal model. And let's go to StatCrunch. Now we can use the normal model. So let's go to the proportion stats, one sample with summary. All right, we found that there was, what did it say? 42 with 30 completed. So there's 30 successes and 42 observations. The hypothesis was 51, and we are purely curious about greater than 51. Okay, and it says 0.01 level of significance. That may not matter. Oh yeah, of course it doesn't matter. We're talking about the p-value. So the test statistic, 2 places, is going to be 2.65. Uh, 2.65, yep. And the p-value is 0.004. Well, that p-value is much smaller than the alpha. So yes, we do reject the null hypothesis because the p-value is less than alpha, not greater than alpha. There is sufficient evidence to conclude it is effective. Okay, so explain the role the sample size plays in the ability to reject the statements. So when there are small sample sizes, the evidence against the statement in the null hypothesis must be substantial. Up here, the evidence wasn't enough. In the first one, the evidence wasn't enough for us to reject it, even though maybe it was close to the same thing, because the sample size 14 is just so small. So one should be wary of studies that do not reject the null hypothesis when the test was conducted with a small sample size. So here, because this test is the small sample size, we did not reject the null hypothesis, which is reasonable because it's such a small sample size. The only way you would really be able to reject it is if you had a lot of evidence, and that's the reason why it says you should be wary of those that don't reject, because maybe they're making up evidence for their case. All right, let's check it. And that's all correct. Very good. All right, a blind taste test conducted. Brand A, brand B, prefer. Okay. Individuals are randomly asked, okay, which to drink 2 types of colas, and then disclose the drink they prefer. 46 of 100 individuals prefer brand A. All right, so now we have to conduct a hypothesis test for a bunch of different things. Okay, so we're assuming that the population equals the proportion and that P naught goes through all of these, or all of these different amounts. So we actually have a bunch of different tests here. Looks like there's like 22 tests. 0.05 is the level of significance. For which values of P naught do you reject the null hypothesis? And what do each of them represent? So we do not reject the null hypothesis for values. All right, we have to do this test for a bunch of them. And the way you can do that, you of course want to use software. Let's see. We do have a population proportion, and I believe we can use the, I guess we can just check that real quick. So if we had 46 over 100, I guess actually we should be using the different, like 0.35 is the first one they're giving us. Yeah, that's the one we should be using. This times 0.65 times 100. That's greater than 10. It's random. I think we can use a normal model without any issues. So that's what we're going to be doing here. All right. The number of successes is 46. Observations is 100. Hypothesis test is 0.35. And it says it does not equal 0.35. All right, let's compute it. You see for this first one, we have a p-value of 0.02. That is less than the level of significance, so we would reject 0.35. 0.35 doesn't work. The next one is 0.36. Same process, same numbers. The p-value here is 0.03, so we would reject 0.36. The next one is 0.37. Compute. And here we have a p-value of 0.06. That's higher than the alpha level of significance. Therefore, we do not reject 0.37. And you continue all the way through. Now, alternatively, what you can do is look at this thing, and instead of doing a hypothesis test, is you do a confidence interval. And the confidence interval is, if it's set to the level of significance, it'll show you what values will be between them. So the lower limit is 0.362, and the upper limit is 0.56, or I should say 0.557. So what you can think of it as is that everything from 0.36 and lower, and everything from 0.56 and higher are rejected, because all the rest of the values, 0.37 like we just found, 0.38, 0.39, all the way up to 0.55, those are all contained within this confidence interval. Therefore, they are contained, they're assumed to be, just variance for being, close to the mean, but they all satisfy the null hypothesis. So we do not reject the null hypothesis between, and again, we're talking about these values here. 0.37 is the first one that's inside the lower limit, and 0.55 is the last one that's inside the upper limit. So 0.37, 0.55. Okay, that's actually what it said here for the lower and upper bound. I just didn't want to go through the whole thing. The lower bound here, 3 places is 0.362. Okay, upper bound is 0.558. All right, suppose you change the level of significance in conducting the hypothesis test to 0.01. What would happen to the range of p-values for which the null hypothesis is not rejected? Why does this make sense? So what we're doing is we're lowering the level of significance, which means we have to say there has to be even more evidence. It has to be more significant evidence to reject the null hypothesis. So what this does is it increases the range of values that would be in the do not reject the null hypothesis, because you have to have even more evidence to reject it. So really what this will do is that it'll increase this range. The lower will go further down, the upper will go further up. It just makes the range of values bigger. So the range of values would increase because the corresponding confidence interval would increase in size. That's the idea. You can also just test this. Instead of doing 0.95, we do 0.99. That's what the same thing as alpha 0.01. And you see the upper limit now is 0.332. It's much smaller. In fact, it contains all of these numbers, 0.588, that contains 0.57. And in fact, there would be no numbers in this range where we would not reject. So we would always do not reject the null hypothesis for all these numbers if we make alpha 0.01. Okay, that's correct. All right, we have a mean random sample of n equal to 40. All right. Let's open StatCrunch. In this case, we're talking about a t value or t stat. We have the summary. Yeah, down here in part B. So let's do part A first. Does the population have to be normally distributed to test the hypothesis by using t-distribution methods? No, because the sample size is 40. If the sample size is greater than 30, then that means it's going to be approximately normal. So no, since the sample size is at least 30, it does not need to be normally distributed. All right, with that done, now we have our mean and standard deviation. That's what I was looking for last time before I started doing stuff. All right, so the mean is 36.1, standard deviation is 9.7, and the sample size is 40. The hypothesis test is equal to 32 and does not equal 32. Very good. So compute. And here is the summary. The t-stat is going to be 2.67. All right. This is mu not equal to 32, therefore it's a two-tailed test. And that's what we're looking for here. The p-value is the shaded region that's greater than or less than the positive and negative version of this, respectively. So definitely not C. C is like the inside version. No, you're looking for the outside stuff. And it can't be A and it can't be D because those are one-tailed tests, which is why B, if I just zoom in on it, you see that it's this area and that area. That's what we're looking for. Those area is the p-value. Okay. Approximate and interpret the p-value. So the probability of observing a sample statistic is as extreme or more extreme than the one observed, assuming H naught is true, is in the range, well, I can show you that in the p-value here, 0.0109. So it's in the range of 0.10, this one right here, 0.01 to 0.02. Now, what I believe this can be done finding the table, not that you need to do this, but we're looking for a t-value of 2.67, which is these values in here. And we are talking about n equal to 40, which means our degrees of freedom is 39. It's always one less. We have 39, and we're looking for 2.67. 2.67 is between these values here, 0.01 and 0.005. But because this is a two-tailed test, it's going to actually be twice this number. So if you're between these values and you double it, that means you have to be between these two values. So any value between these two, like for instance, because we know it's going to be between them. So for instance, like if it's 0.006, let's say that's what it was, then if you double 0.006, you get 0.012, which would be between these two values. That's the key thing to note here, is that if you have a one-tailed test, then it would be in this range. A two-tailed test, you just double that and you get to this range. So that's another way of looking at this one. Let me just make sure this is correct. I think it is. A sample statistic, we're not talking about the population, we're talking about a sample, is as extreme or more than. That's the reason why we're talking about the as extreme or more than. That's what those areas are showing. And assuming H naught is true, you always assume H naught is true and then go from there. And that's what you get. So if the researcher decides to test the hypothesis at 0.01 instead of the... we don't have it yet. That was the first time we talked about alpha. Will the researcher reject the null hypothesis, and why? Well, the p-value is between 0.01 and 0.02. And the level of significance is 0.01. the p-value has to be less than the level of significance to reject the null hypothesis. In this case, the p-value is greater than alpha, so we fail to reject, or we do not reject. Okay, construct a 99% confidence. That should be easy with this. We just go for a confidence level and make 99%, or 99% confidence. And now we can see our lower and upper bound. 3 places, so 31,947. And then 40.253. Okay, and what was the value again? 32, of course. Because the value 32 lies within the confidence interval, we fail to reject the null hypothesis. Same process. If the p-value is greater than alpha, we fail to reject. If it's contained within the confidence interval, we fail to reject. And then vice versa. If the p-value is less than alpha, we do reject. If 32 was not contained within the confidence interval, then we also reject that. Let's test. And those are all correct. All right, college entrance exam, determine the score of 22 in the mathematics proportion. To achieve the goal, companies recommend. Okay, we have a random sample of 250 students. Results in a mean math score of 22.3. Standard deviation of 3.8. The results suggest they are ready for it. That is, are they scoring above 22 in the math portion of the exam? Okay, so we're going to state the appropriate null and alternative. So a college entrance exam company determined that a score 22 is ready. So that's what we're starting with. Is we're saying, in this case, is it the sample statistic, or is it the mean? Yeah, so when you're doing this, you're always talking about the population, in this case, population mean. Before we were talking about population proportion. That's why it's mu. X bar, this is the sample mean. So we have a sample, but it's not what we're talking about as the full population. So here, the null hypothesis is where the mean equals what's already been given, 22. And the alternative is saying, are they scoring above 22 in the math portion? So is actually this greater than 22? Okay. So verify the requirements to perform the test using t-distribution. So t-distribution just says we need greater than 30, which we have. And I believe we need randomly sampled, which it said it was. I suppose a random sample, yeah. I think we also need independence. I think you always need independence. And that is, let me check to make sure on that. I just wanted to show this real quick. Sample is simple random sampling or from a randomized experiment. The sample size is large and that they are independent. You always need independence for these. So yeah, I should have assumed that. And they are independent because one student's score shouldn't affect another student's score in any way, since they each are doing their own test. And they can't share a test because they probably take it at the same time. So I think we can verify the requirements and we can go forward from there. So p-value using a 0.05 level of significance. Let's open StatCrunch and the stats. See, we have the summary, right? Yep. Okay, the mean is mean math score of 22.3. Standard deviation of 3.8. I think the sample size said it was 250. Yes. So the hypothesis is that it equals 22, and we're looking for if it's greater than 22. Compute that. Okay, the test statistic is 1.25, and the p-value for that is 0.107. And so the conclusion based on these results, well, p-value is less than the level of significance, greater than the level of significance. Therefore, there is not sufficient evidence. We do not reject the null hypothesis and claim that there is not sufficient evidence to conclude that the population mean is greater than 22. There's not sufficient evidence, so we're still assuming that that mu equals 22, in other words. That's all correct. Okay, the mean waiting time. So mean tells us it's going to be, mu instead of a population proportion. Is 83.8 seconds. Manager devises a new drive-through system that she believes it will decrease wait time. So decrease is what we're looking for here. As a test, we have randomly selects 10 orders. We have 10 orders here. Wait times are provided at the table to the right. Okay, so first off, 10 randomly selected orders. That should say to you, oh wait, that's too few. We can't use any hypothesis testing for this. That's why part A is here. Part A, it says because the sample size is small, we must verify that it's normally distributed. And we can do that by using the correlation. This is back in chapter 5, or chapter 4 or 5. The normal probability plot is shown below, and the sample correlation coefficient is known to be R equal to 0.995. It's very high R value, right? R was I believe R is between -1 and 1, or between 0 and 1, whatever. Anyways, if it's very close to 1, that means it is very linearly correlated, and that's what we can see here. This is pretty much a straight line. So yeah, that makes sense why it's so high. So are the conditions satisfied? Well, we can use this table, and it says sample size is 10, and the critical value is 0.918. If this value is greater than that, then that means it is the hypotheses are satisfied, and this is, right? So yes, the conditions are satisfied. The normal probability plot is linear enough since the correlation coefficient is greater than the critical value. And you can see in the box plot, if you did a box plot here, I can show you, I believe. Doesn't look to be very many outliers, if any. So it's all kind of contained in this graph. All right, so with that being said, we can move on and actually do the hypothesis testing. So first off, we have a mean is equal to, of course, and we're looking for not the standard deviation, the mean. She believes it will decrease the wait time, so we want this to be less than the mean wait time. Okay, to do this test statistic, we have to take the data. I should have left it open when I was doing that before. And we now, this is a t-value because we're talking about a sample, and we have data here, not summary data. var1 is in our data. That's the first column here. The hypothesis testing is 83.3, and we want less than that. I don't think I need anything else there, so let's compute. All right, the t-stat is negative. Don't think that it needs to be negative. I think we can put that as positive. Or no, it's less than, never mind. Of course, it's negative. Negative 1.23. P-value is 0.125. And with a level of 0.1, obviously p-value is greater than 0.1, therefore we fail to reject. Since the p-value is less than, There is not sufficient evidence. It has to be greater than, or sorry, less than the alpha for it to work. The p-value is greater than. There is not sufficient evidence. I was about to do something different. Okay, p-value is greater than. There's not sufficient evidence to conclude this new system is effective. All right, that should be all correct. All right, let me just see what I did wrong. Okay, I'm not really sure what happened there. I did the same thing, I think. One sample. I might have hit Z stats. That might have been the problem. But 83.8 is less than. Cute. And when I do it this second time, I get a different T stat. So I'm guessing I clicked something instead. I didn't see it say T or Z. But the test statistic here is negative 1.35. 1.35. And that changes our p-value to be 0.1056. I believe in 1-3 places. Yeah, 1056. So it's going to be 106. That doesn't change the conclusion, though. The p-value is still greater than the level of significance, and so that there is not sufficient evidence. So we check that, and now it's correct. Sorry about that confusion there. Okay, moving on. We have a simple random sample. N equal to 200 drivers, 200 survey, 107 responded that they did drive a car manufactured in a certain country. Determine if more than half of all drivers made in this country drivers drive a car made in this country at a 0.05 level of significance. So first off, this is a proportion because we're talking about a proportion of drivers doing something. So this is going to be equal to 0.5, more than half. So we're going to be greater than 0.5. Okay, the p-value, let's see, it doesn't really matter. We can just delete this column. Go to data. This is going to be with summary. I guess we should really test to see if everything's it's simple, or sorry, it's random. It says a simple random sample. It should be all be independent of each other because the survey is random. And if we do, let's see, N is 200 times 0.5 times 0.5. That's P times 1 minus P. We get 50, which is greater than 10. So we can actually do this. The number of successes it said was 107. And 200 observations, 0.5, greater than 0.5. Let's compute that. All we care about here is the p-value, 0.161. And that should tell you what you need to know for the conclusion. It is not greater than 0.05. Therefore, we do not reject it. P-value is greater than 0.05. So there is not significant evidence. And that's all correct. Last question we have, according to a recent article, individuals have credit cards. The mean number of credit cards a person holds is 4. They test 60 individuals in a random survey. Again, they should all be independent because they shouldn't be related or anything. They should how they did the random survey, I'm sure, would have included that. So first off, I'm just going to test this real quick. Or wait, no. This is a... It's a mean. I was just going to test the population proportion. But this is a mean number of cars is 4. And they're working with 60 individuals. That's greater than 30. Therefore, we can use the normal distribution to approximate it, and we can use the hypothesis testing. So the variable of interest is the number of credit cards. So that would be a quantitative variable because it's a number. It's not a like a color or something like that. It's a number. Okay, so do the results of the survey imply the mean number of cards is less than 4? Is less than 4. So we're assuming it equals 4. The mean equals 4. And we want to know, is it less than 4? All right. I was looking for the mean and the standard deviation, but that's because is right here has the data from the survey. So we just open up the data and open it in StatCrunch, and we do a t-stat distribution with data. So var1 hypothesis equals 4, and it's less than 4, and that should be all we need. So the t-stat is negative 0.55. P-value is 0.292. P-value is greater than the level of significance. We do not reject the null hypothesis. There is not sufficient evidence to claim the mean value is less than 4. And that's all correct.